Hello, back to lesson 4 of the same unit. Currently, this is called unit 6. We're going to be solving or proving or simplifying trig equations. However, in this case, we'll have to use identities. Now, my previous two videos, the last video was proving these identities. I've made a table of all the possible identities that we're going to be using. But in the previous video, I proved them all, or I showed them how they're derived. You will not be tested on how they're derived, but we're gonna be using these identities to prove some other equations. I would like for you to not get overwhelmed with this lesson because proving these using the identities, every question is like a puzzle. There's no set way to do it. Like I could be working on proving an equation using these identities, and halfway through I might realize that, oh, that's not gonna work. So I might have to restart it. That happens with everybody. Don't feel bad if you're not able to prove it in the very first go. So one more time, these are Pythagorean identities, three of them. These two are the ratio identities, and then we have the reciprocal identities. At the very bottom, the three listed in blue, these are the even-odd identities. Uh, Sine is an odd function, so this one's odd identity. Cosine is an even function, and tangent is also odd function, hence the negative stays. So let's go ahead and get started with some examples. Let's start with something basic. Like this question says simplify, which means I'm not proving, I just have to simplify this ratio as much as I can. Cotangent theta over cosecant of theta. Basically, I'm trying to simplify it. Also, simplifying answer is going to look shorter and more relevant than what we're starting off with. Because we're simplifying it, we're not going to make it any harder than what it is. For example, 5/25 when simplified is 1/5. So obviously this looks smaller. Our brain makes a better connection with 1/5 than it does with 5/25. Just as an example. Okie dokes. So when I look at the numerator, I also see that cotangent can be simplified as cosine over sine theta. So I'm going to go ahead and do that over sine theta. The idea is cotangent and cosecant. Like cotangent, what were the other three? Cosecant and secant. These are inverses of tangent, sine, and this one's inverse of cosine. Generally, these will be reduced to these three because the first three are considered to be more simplified. So I'm going to start off by replacing with that. Then cosecant, which is, where's cosecant at? Right here. Cosecant can be written as 1 over sine. So that way cotangent and cosecants are gone. I'm going to just replace this with 1 over sine theta. It does look complicated at this time. I have a ratio over a ratio, but we've done this enough in class to where you know that if the denominator of the numerator and the denominator are the same, they can be canceled. That also works with the numerators. So this cancels, which means I'm just left with cosine theta over 1, and then obviously there's no need to write that 1. And I have simplified it. If you look at the question and look at the answer is way simplified. Honestly, it worked out the very first time. Let's move on. Check out some other example. This one's slightly different. This one says, prove this, that cosine over 1 plus sine theta is equivalent to 1 minus sine theta over cosine theta. So we have to prove this. Now notice this, there's a left-hand side to this, and then there is a right-hand side to this, correct? Which was not the case in the previous example. So when there's a left-hand side and a right-hand side, and it's a proving question, there is a rule to this. We cannot start with both the sides, which means I can't start working with this side and simultaneously be working on the right-hand side. And if the simplified version here equals the simplified version here, that is not considered to be a proof. Number one. So that's the no. Can't do that, can't do that. We can only work on one side at a time. So if you choose, and you can pick and choose whichever side you want to work on, but if we decide to work on left-hand side, then we will keep working on left-hand side. And at the very end, if the left-hand side looks just like the right-hand side, we have proved it. That's acceptable. You've got to start with one side only. Again, like I said, you can pick and choose the side you want to work on. If you look at this question, they both look about the same difficulty level. The right-hand side doesn't look more difficult than the left and vice versa. So I'm just going to go ahead and get started with the left-hand side. I'm just rewriting it here. Now there's cosine and sine in it, which are already simplified. I don't want to change sine to cosecant and cosine to secant just because they're reciprocals of each other. This one's already simplified. No, I take that back. I can't really change sine and cosine into anything. And this is very new, so please be patient. What I'm going to do is, before I proceed, let me remind you a very important algebraic formula that you were very aware of. This is called difference of squares. A squared minus b squared is called difference of squares, which means if I were to factor it out, you write the first and the second, and the first and the second, one with a plus, one with a minus, and we have factored it out. So if you're given something like this, we can compress it to make it look like difference of squares. And if we have different squares to begin with, we can factor it out and make it look like right-hand side. So keep that in mind, where a and b can be anything. What I'm going to do here is I'm going to go ahead and multiply by 1 minus sine theta, 1 minus sine theta. So technically when I do this, I have multiplied by 1, correct? Which means I haven't really messed with the equation. Multiplying by 1 does not change the original equation or ratio. So mathematically, this is correct. Now, why do I do that? I'm doing this to introduce difference of squares on purpose. So if you look at the denominator, the first one looks like a plus b, and the second one looks like a minus b. And we did that on purpose. So if I go ahead and continue with this, in the denominator, I have 1 plus sine theta times 1 minus sine theta. And it's multiplication, so I really don't have to worry about making the denominators look the same. In the numerator, it's cosine theta times 1 minus sine theta. Now, don't be thinking of going ahead and canceling these. I mean, we can cancel them, but we will be back to our original question. The reason we did that was because we now see a plus b, a minus b in the denominator. That's your a, that's your b, that's your a, and that's the b. Which means this can be simplified as a squared minus b squared. A is 1, so 1 squared minus sine theta squared, and the better way to write that is sine squared theta. It's the same thing as sine theta whole squared. Theta is not squared though, be careful. And I still have cosine theta times 1 minus sine theta in the numerator. I can go ahead and distribute this. If need be, I'll do that. I don't know yet if I need it or not. And then if you notice, I'm pretty much rewriting everything. I'm just saying that 1 squared is basically just 1. Right? I haven't used any identity yet, but, watch this. Boom, 1 minus sine squared theta. That's an identity. That identity is not listed directly. That's another thing that you will learn as you practice these more, but this is the same identity as the very first Pythagorean identity. If you watch my last video, we saw how it's derived. Sine squared theta plus cosine squared theta equals 1. Like, how do I know it's the same identity? Let me rewrite it. Sine squared, and also in the last video I showed that you can write this same identity in a few different ways. Let me subtract sine squared theta from both sides. And that leads to cosine squared theta is equal to 1 minus sine squared theta, which means 1 minus sine squared theta can be replaced with cosine squared theta. And that's what I'm going to do now. In the denominator, 1 minus sine squared theta will be replaced by cosine squared theta. What have I used here? A Pythagorean identity. And numerator still stays the same. I chose not to distribute, and guess what? That was good for me because I now see that cosine theta will cancel with one of the cosines here. Let me tell you something. How about cosine squared theta I'm going to rewrite cosine squared theta as cosine theta times cosine theta, right? We can do that, right? X squared is the same as x times x. Now you can see one of the cosines will cancel with one of the cosines here. What does that leave me with? 1 minus sine theta over cosine theta. Guess what? Have a look at the right-hand side. Well, what's right-hand side? Yep. I have solved left-hand side, and I have made it look like right-hand side. This is equal to right-hand side. And the most satisfying thing here to write is hence proved. I have proved it. Yep. If it's very bizarre, if you're like, oh boy, what just happened? Just be patient. Like I said, this needs practice. If I were given a very complicated identity or equation to prove, it's quite not possible that I may not get it the very first time, like I said. So feel good about yourself. It's a learning process. Let's see, what do I have next? Here's another interesting one. Just from example 1 to example 3, we accomplish a lot. 1 plus sine of x. This one's using x. It doesn't matter, alpha, beta, gamma, x, theta, yada, 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 fancy stuff. X is an input. They are wanting me to, oh, this is an add question, like plus, and the denominator is cosine x, cotangent x minus cosine of x. Whoa, whoa, whoa. They're saying solve it. It's not an equation, so there's nothing to prove. Solve and simplify. So get it as simplified as possible. Trust me, the final answer is going to look really, really nice and sleek. So this is together and that's together. And it's an addition kind of question. So with additions, we got to be careful. Our numerators and denominators, the denominators have to be the same. So I could go ahead and add them, which means I'm going to make them the same now. This one needs sine theta, right? Sine x. I'm going to go ahead and give it to it. And then I also have to multiply the numerator by sine x. On the other side, this one needs to be multiplied by cosine x. Hence, numerator also needs to be multiplied by cosine x. Okay, hopefully so far so good. Which means, what do I have in the denominator? In the denominator, I have sine x times cosine x. Same denominator. And in the numerator, I have cosine x times 1 plus sine x plus cotangent x minus cosine x times sine x. Be very careful. You have to distribute all of these. And clearly, I'll have to distribute here. It doesn't look like anything is going to get canceled, so I'm going to go ahead and distribute that. Cosine x plus cosine x times sine x. Okay, done. And then plus the sine x needs to be distributed, both of these. Minus cosine x times sine x. When two trig identities, if functions are written next to each other, they're by default multiplication. So it's cosine times sine x times this, so that was just sine x. Over sine x times cosine x. Okay. In the numerator, do you see something starting to cancel? Sine, cosine, minus sine, cosine. It's the exact same thing, different signs. It's just perfect. They cancel. That's so satisfying. Then I have cosine x plus cotangent x sine x. You know what? Just from experience, I do know that cotangent x is an identity where cotangent is the same as cosine x over sine x. That's the reciprocal identity. There are only two of them right there. So I'm going to go ahead and use that. And that triggered me just because I know that after I replace cotangent with cosine over sine, the signs will cancel out. So I'm going to go ahead and do that. Let me finish this off first. Times cosine x. Also, if you're getting tempted to go cancel these two, you can't. Or cancel these two, we can't. we cannot cancel parts of a polynomial with part of another polynomial. They have to cancel like all together. For example, if I had cosine, like in the previous question, there was a cosine x, and then there was cosine squared x, and then there was 1 plus sine x. So this was a monomial, and that's also a monomial. Hence, I could cancel part of this with part of this. Not otherwise. If they are separated by a plus or minus, you can't. So watch this now. Plus cotangent, I'm going to write as cosine over sine times sine in the numerator. And it's so satisfying because these two cancel. Don't forget there was still a denominator. Cosine x. Now what's in the numerator? Well, there's a cosine x plus cosine x over sine x times cosine x. Please, again, you cannot cancel the cosines yet. But what we can do is, the numerator, that we have like terms, cosine x plus cosine x. It's not cosine squared x. They add up to 2 cosine x's. Just like x plus x is not x squared, x plus x is 2x instead, similarly. And then I have sine x times cosine x. And guess what? Here is when I can cancel cosine and cosine, because these are not separated by plus sign or minus sign. There's a multiplication sign in between them. I also forgot to write x here. There we go. Cosines have canceled, and now all I have is 2 over sine x. That's the farthest we could go. It looks very, very simpler as compared to the original question. So we have simplified our third example. All right. We started off with making the denominator the same because it was a plus type of question. Once the denominator was the same here, then we had to go ahead and distribute these carefully. And when we distributed, it just happened so that these two terms canceled. One was a plus, one was a minus. That was awesome. Then the cotangent had to be, once cotangent was replaced by its reciprocal identity, the signs happened to cancel, which is great. Canceling is good. Then we had cosine, and we added them to 2 cosine x in the denominator. We still had this, and the cosines canceled, and this is where we were at. All right, I have another question. Yeah, well, you know what? I think I'm gonna stop the video here. It was a pretty long video, so I'm gonna make another video with the other ones. Alrighty, 3 examples. Hopefully some of it made sense, or else we'll practice and we'll get better. See you then.